Sum of tensors. In this video, we'll define the sum and product of tensors, plus we'll go through examples to solidify your understanding. If you're ready, let's go! Please subscribe to my channel to receive notifications when new videos are uploaded. Let T and S be two tensors. The sum of T and S, denoted by T plus S, is defined by T plus S times A equals TA plus SA for any vector A. It is easily seen that T plus S is indeed a tensor. Let W equals T plus S. Using equation 275, the components of W can be computed as Wij equals EI dot Wej. We replace W with T plus S. We distribute T plus S into Ej, and then Tej plus Sej into Ei. Ei dot Tej equals Tij, and Ei dot Sej equals Sij. Therefore, Wij equals Tij plus Sij. Also, we can write it in the matrix notation. Product of two tensors. Let T and S be two tensors and A an arbitrary vector. Ts and St are defined as. It states that when you multiply the tensor product of T and S by a vector A, it is equivalent to multiplying T by the result of the tensor product of S and A, and the same for the tensor product of S and T. Now, how to calculate the components of Ts and St? As before, we can write the ij component of Ts as the dot product of Ei and Tsej, now using the above definition. And using the equation 272 from the previous videos. Smj is a constant scalar, so can be taken out. This equals Tim. And finally, we will have Tsij equals Tim Smj. This expression highlights how individual components of T and S contribute to the ijth element of the product tensor. Similarly, Stij equals Sim Tmj. In matrix notation, we can write. In general, Ts is not equal to St. Therefore, tensor product is not commutative. If T, S, and V are three tensors, then we can write T applied to the tensor product of SV and the result applied to the vector A. From the definition, we can write it as T applied to the result of the product of SV and A. This can be written as S applied to VA from the above definition, so it equals T applied to the tensor product of S and VA. Also, Ts applied to VA from the above definition is equal to T applied to the result of the product of SV and A. Star 1 and star 2 imply that. Therefore, the tensor product is associative. Integral positive powers of a tensor. Using the associativity property of tensors, we can define the integral positive powers of a tensor as follows. T square is equal to the tensor product of T with itself. Cube of the tensor T is equal to the tensor product of T with itself 3 times, and so on. The fourth power of the tensor T is equal to the tensor product of T with itself 4 times. Let's see some examples. Let R correspond to a 90-degree right-hand body rotation about the x3 axis. Find the matrix of R. Let S correspond to a 90-degree right-hand body rotation about the x1 axis. Find the matrix of S. Find the matrix of the tensor that corresponds to the rotation R followed by S. Find the matrix of the tensor that corresponds to the rotation S followed by R. Consider a point P whose initial coordinates are 1, 1, 0. Find the new position of this point after the rotations of part C. Also, find the new position of this point after the rotations of part D. Solution. For deriving the tensor R, we should see how it transforms the unit vectors. The transformation of E2 is minus E1, and the transformation of E1 is equal to E2. Let's write down these equations and construct the rotation matrix. We construct the tensor S as we did for the tensor R. For constructing the tensor R followed by the tensor S, we can write. So, the target tensor in this part is the tensor product of S applied to R. In the matrix notation, we can write it as and the same holds for the rotation S followed by R. In this case, the target tensor is Rs. As you see, SR and RS are different. Suppose R is the initial position vector of point P. R star is the rotated position vector of R under SR, and R double star is the rotated position vector of R under RS. So we can obtain R star and R star plus as follows. Notice that the results are different and the order of rotations is significant. In the next session, we will see the transpose of a tensor. Thank you for watching. Please subscribe my channel.